computer? All righty, and we'll go ahead and get started. I thought we would start off today with just kind of asking if what people thought of the planetarium and if anybody had any comments or questions after getting the chance to go and hang out and see what we would have seen in the night sky and learn about precession and some other things as well.
I thought the presentation was excellent, and I learned a fair amount. The planetarium is terrific. They could probably use chairs that lean back a little bit. But other than that, it was really a great evening. Thank you for it.
You are most welcome. And I was so sorry that we didn't get a chance to do any observing, but it was darn cold. I think that we would have froze. But good. I'm glad you enjoyed. Hey, I like the artwork behind you.
Thank you. That's my daughter.
Very beautiful. And anybody else have any yes, okay. Mauricio.
Yes, hello. Yes, it was lovely. I really loved seeing the stars and the planets in the planetarium, and it also gave us the opportunity to meet the people who run it, particularly Dr. Harold Williams, who shares my interest. Well, of course, he knows a lot more on astrolabes. And he has a few astrolabes. He has built some astrolabes, and I've been enamored with them for a very long time. And astrolabes are a very good way to learn astronomy and also to pique your curiosity and find out more things about it. So once you use the astrolabe and start finding stars, etc., you want to know more about them. So I really love the instrument and really keen to be able to build one now.
That's a great idea. I forgot all about astrolabes, and you are so right. When I used to teach astronomy to kids, I would have them, create some of the things and do some of the things that the early astronomers did to understand how we got to where we got to now, which, some of what I'm going to talk about in a little while. And so by taking those tools of old, that we actually can get out there and use, that is a great idea. I'm going to have to look into that because that would be make myself a note. That would be a fun thing also to do and then do with with my grandkids and show them, how it works.
Yeah, because it is a planisphere like the ones we use to actually find stars in the sky, etc. But this one can do a lot more, a lot more things. So that's what makes it so interesting.
That's neat. And I'll tell you, Harold, he is an amazing man. He is a character, an absolute wonderful, amazing character. And I have sat down on many occasions and just let him talk and
Yes.
learned so much on so many subjects. He's definitely one of my favorite people, and I hadn't known that he would be there. So I was so pleased that he was. That was really nice.
Yes, and you're quite right that you have to let him speak. It's very difficult to actually interject.
Yes, indeed. The
Thank
the
you very
old
much.
Oh yeah, the old planetarium before they fixed it up so nicely, it was actually really neat. It was kind of like going back in time, and Harold had just all kinds of things in there. I loved it because it was just filled with, homemade things and, like you say, astrolabes and sextants and just any number of things. And he could just go over and he knew exactly where everything was. It was kind of like if you watch like Hagrid in his special place. That's how it was with Harold. Just a really unique individual. So good. I'm glad you appreciated him. That's
Very
cool.
much so, yes.
Awesome.
Dorian, this is Annabelle. Hi. How is that word spelled? It's astrolabe, Laeb.
Labe.
Okay,
Yeah.
thank you.
Astrolabe. You're welcome. Yes. And I wanted to show, did anyone else actually, before I show you something, before we get started with the official class, did anyone else have any comments?
Well, this is Dan. Unfortunately, I forgot and I arrived late, so I missed most of the presentation, but it was, good to know that the planetarium exists. I now know where it is and understand that they do make presentations periodically, so I will be following up and attending some of those. So it was beneficial for me, but not nearly as much as it could have been had I remembered earlier to
It was so nice to
arrive.
meet you, and next time.
Yes, yes.
And that's actually a perfect segue into what I wanted to show you all. I went and did a little bit of research on, so I'm just going to skip down to here's our class tonight. I've already put the presentation slides, and of course, once we're done, I'll put the recorded lecture. But underneath all of these different links that I gave you that are related to today's topics, I put on here some websites to some places where you can go and either do observing, or sometimes they have activities that they do. So I put all of those different links here. And then here's the Montgomery College, and the one that that Cassie had been talking about. I told her I'll keep in touch with her, and I want to find out when they open again at their Rockville Observatory. And then I will reach out and let everybody on whose email I have in this class know, and maybe we can meet up sometime in the warmer weather when they have opened up that observatory. And then down here, I put a couple of other things. I've never heard of Thrill List, but as I looked through their top 10 places to stargaze, it looked pretty good. And then this one, the National Capital Area Astronomers website, that is, you're going to find all kinds of neat things on there, including lectures and that sort of thing. So it is something in this area we definitely have access to just an amazing amount of cool things. So I wanted to show that to you. And then there was another thing I wanted to share. Let's see how to get to that. Let me stop this for a minute. Oh, it's intent on sharing. There's going to be a kind of a planetary alignment that's going to be coming up. And so I found a video on that. Let me close this here to come to, and close that there. Find my movie, close that there. Okay. Unbury all of these things. Share that, share that. And this will tell us a little bit about this this upcoming planetary
I don't know
alignment.
about you guys. I'm a big time space nerd, and this is going to be fantastic this week, okay? This week, we'll be able to look up at the night sky and see 7 planets, 5 with the naked eye, 2 of them you'll need binoculars for. But here's exactly what they should look like in the night sky. We'll have Mars, Jupiter, Uranus, Venus, Neptune, Saturn, and Mercury all visible this week, with the best view tonight and tomorrow night. Now, the best time to go out there, of course, tonight and tomorrow night, but also visible Wednesday and Thursday. The alignment itself will be best tonight and tomorrow night. The brightest stars will be Venus and Jupiter, but you will need a telescope if you want to see Uranus and Neptune here. They will not be visible with the naked eye. Now, the one issue with tonight is that we will have the cloud cover.
All right, I'm going to close that there. But so, and it also, if you look at those, the links that I had shared from, I think it was from the first week, where I showed the the ways in which you can look at the night sky. That will be a big help in knowing what you can see in the night sky. So, without further ado, I will go ahead and get started with tonight's course. So what I wanted to do first is I just wanted to see if there's any questions, any muddy water that anybody had. And then I want to talk a little bit about why conduct research on space. So give some a couple of different examples of some of the ways in which that information is useful, not only for learning about space, but also for us here on Earth. And then going to talk about ground-based versus space-based telescopes and some of the pros and cons of each of those, and then some of the research that's being done with each of those. So first I'll see, though, I didn't give enough wait time. Were there any questions that anybody had that I should try to answer first? All right, we sound okay, enough wait time. Okay, so why study space? Well, of course, it always intrigues us as to whether or not there is life out there. And I'm going to tell you a little bit about that. We're going to look at something called Drake's equation and cover a little bit more information related to that. But before I get into looking out there and to see if there is possible life, one of the reasons that we study space is to better understand this crazy old universe that we live in. And when you think about the fact that, we used to go from thinking it was a geocentric, universe and having no idea what was really out there. And then you look at the information that we have now and how we really don't even fully understand what is happening out there. There's lots and lots of theories as to the shape of the universe and things like the expansion of the universe, the idea of dark matter, dark energy, trying to understand these concepts, these things that we don't really know much about. So I thought I'd start off by showing a little bit about the history of the universe. Now, question, can you see right now where it says cosmic history? I can't tell if you're seeing my the link I pushed or not. Just give me a thumbs up, Dan, if you can see it.
I'm not, no.
Okay, cool, no problem. Let me just make this small and let me go here and come back to my share. They're just going to make it difficult for me. That's okay. I'll make it work. Okay, so in looking at cosmic history, going to come over here and just take a look at this diagram here. And, of course, this is what we call theoretical astronomy, theoretical physics. This is based on the information that we have right now, what we believe to be true. And so, you always hear about the Big Bang and this idea of this initial inflation. And then in like 1 microsecond, then within 3 minutes, kind of looking at the fact that neutrons, protons, and electrons formed from that huge burst of energy. And then you start to have your helium and your hydrogen. And then it took about 300,000 years for the first atoms to form. And then our stars started about 200 million years ago. And so this is in the entire universe, not just here in our galaxy. Then it took about 400 million years for galaxies and dark matter. And a lot of this is based on spectroscopy, which is basically, and we'll look at some of these different types of telescopes and learn how they're able to get this spectral analysis of stars and even understand about how far away they are. Going to see a video that helps us understand that in a minute. So then galaxies and dark matter, and then this dark energy, which we don't know much about, but part of what we know is that we've got the universe is expanding. We also know that there's black holes which are pulling things back in. So you and it's kind of neat because with nature, it's always kind of seeking to find an equilibrium of some sort. So we've got this expansion and we've also got this contraction, but the expansion is stronger than the contraction. And in the video that we'll look at, we'll get a feel for why that is so. So here, about 13.8 billion years ago is when humans started to observe the universe. And that's where we are today. were, so it's not the first time we started to observe the universe, but it, wasn't that long ago that people actually understood this concept that there is this whole universe. So you can, this is one of the sites that I have put up if you want to learn more about the universe's history. And I'm going to close that for now. And I've got to bring up for myself a Word document that is hiding somewhere that has my notes. All righty. Let me make sure, come back here to you guys. And make sure that I'm showing you what I want to be showing you. Sorry about that. Sometimes Zoom can be a little bit tricky, at least on my end. Okay, share. I want to come back to sharing the PowerPoint and share. And I want to do it from the current slide. Okay, so we have that. And then I talked a little bit about this expansion of the universe. So let me stop that. Come back here. Come back here. And here. And there.
The universe's expansion, which was first introduced by Edwin Hubble, remains one of the most significant puzzles in cosmology. Although we know the universe is expanding, measuring the precise rate of this expansion has led to conflicting results, a challenge referred to as the Hubble tension. So, could Webb finally help us unlock the secrets behind the universe's expansion and bring clarity to this cosmic mystery? In this video, we'll explore the Hubble tension, the role of the James Webb Space Telescope in addressing this mystery, and what it could mean for our understanding of the universe. The Hubble tension is a major challenge in modern cosmology, centered on conflicting measurements of the Hubble constant, which is the rate at which the universe is expanding. This debate traces back to Edwin Hubble's 1929 discovery that the universe is expanding, which revolutionized cosmology and led to the development of the Big Bang theory. Over time, two primary methods for measuring the Hubble constant have emerged, producing divergent results. The first method analyzes the cosmic microwave background, the residual light from the Big Bang. By studying this ancient radiation, scientists estimate the universe's expansion rate during its earliest moments, which has yielded a precise Hubble constant of around 67.4 kilometers per second per megaparsec. The second method focuses on more recent cosmic history by observing the expansion rate of nearby galaxies. By calculating their distances and recession velocities, astronomers derive a higher Hubble constant, roughly 74 kilometers per second per megaparsec. This discrepancy between the two measurements, known as the Hubble tension, suggests that something significant might have altered the universe's expansion over time, or it may point to new physics beyond our current understanding. The tension challenges the lambda CDM model, which has otherwise successfully explained phenomena like galaxy formation and the distribution of cosmic structures. Webb's infrared light penetrates cosmic dust more effectively than visible light, enabling it to capture clearer images of stars and galaxies that might otherwise be obscured, which is pivotal for measuring the Hubble constant using different types of stars and comparing those measurements across different cosmic epochs. Wendy Friedman and her team at the University of Chicago utilized Webb to observe 10 nearby galaxies, focusing on 3 distinct types of stars to measure the universe's expansion. The first method they employed involved Cepheid variable stars. Cepheids are a type of star that pulsates at regular intervals, with a direct relationship between their pulsation period and intrinsic brightness. So the strategy is measuring the apparent brightness of these stars and comparing it to their intrinsic brightness so that astronomers can determine their distance from Earth. This, in turn, allows for the calculation of the Hubble constant based on how fast these galaxies are receding from us. The second method used by Friedman's team is known as the tip of the red giant branch, TRGB. This method focuses on a specific stage in the evolution of low-mass stars, where they reach a consistent maximum brightness before transitioning to the next phase of their life cycle. This method provides a reliable distance measurement, especially for older, more evolved galaxies. The third method involves carbon stars, which are characterized by their consistent brightness in the near-infrared spectrum, making them excellent candidates for distance measurements using Webb's infrared capabilities. What makes this study groundbreaking is the simultaneous application of all three methods within the same set of galaxies, which allowed for cross-verification of the results, reducing the likelihood of errors or biases that might affect the measurement of the Hubble constant. Remarkably, the values obtained from these different methods were consistent with each other and aligned closely with the CMB-based measurement of the Hubble constant, around 67.4 kilometers per second per megaparsec. This suggests that the discrepancy observed in previous measurements might be narrowing, potentially reducing the severity of the Hubble tension. If future observations continue to support the alignment of these different methods, it could indicate that the Hubble tension is not due to a fundamental flaw in our understanding of the universe, but rather a result of the challenges inherent in measuring such vast cosmic distances. However, if discrepancies persist, it might suggest that new physics or unknown cosmic phenomena are influencing the universe's expansion.
I mean, like, how crazy cool is that? And wouldn't it be an amazing time to be, an astronomer, to be somebody who is working with the James Webb and the Hubble telescope? And when I tell you a little bit more about these telescopes, you'll get a feel for the ways in which you don't necessarily just use one of them. Lots of times, in order to make these discoveries, they need to use a couple of the different telescopes and gather data from various places. So my goodness, absolutely crazy how much knowledge is and the way that technology is being used now to better understand the universe. But also, anytime you've got good science, whatever science you have raises more questions. Yes, and I see there's a hand up. Feel free to unmute.
Marty here. I just have a question, and without getting into, the detailed physics, since I've never taken a physics class, they're saying that the universe is expanding because the masses are moving away from Earth. And they know that, do they know that it's expanding, or versus the planets are moving away from Earth, but in a finite area?
Sure.
I mean, if you have a big enough area and they're moving away, they're still moving, but it's a finite area that they're moving from.
That's a great question. And the thing when we get into talking about like things like the universe is we are really into theoretical physics, because it's kind of like you say, we can't really experience it. We haven't even been able to send, any spacecraft far enough that it could actually even get into the atmosphere of, well, one of a spacecraft has finally got into the atmosphere of the next closest star. But, so we're talking about huge distances away. But we are able to get information not just on the planets near us, but also those galaxies, and even further back, those Cepheid stars they were talking about, and even see not just how fast they're moving away from Earth, but by looking at the distances between where the Cepheid star was and where it is, say 3 years later, or however many years later that they're looking at it. I believe that that's how they're able to say that it's not just relative from our place on Earth that things are moving, but also relative to each other. And when they're talking about the universe, they're pretty much talking about it being infinite, which is beyond my real understanding, but that the universe is kind of expanding infinitely. There's, nobody knows for sure the answers to this. I know for a while when I was teaching middle school and high school astronomy, I had some students who were very adamant that, God created the world. And I said, you know what? In the beginning, there was light. So, if that narrative does not negate this Big Bang theory, because certainly in the beginning, as all of this happened, there was light. So it's kind of neat how those two narratives don't have to be, exclusionary. And the kids always kind of were like, wow, I hadn't thought about that. Now, the 7 days and 7 nights thing, there's where you run into some problems. Another thing I was going to say is one time, of course, not everyone, most people believe in this idea of the Big Bang and inflation. But I one time heard a very prominent astronomer who had this idea that there was actually a recycling of the universe. And certainly, we see recycling happen when trees die and they go back to the ground and become, leaf litter, and then new trees are born. So his idea was that the universe had kind of expanded so much, kind of like a balloon. And sometimes that's how we explain the universe, put little dots of on a balloon with a permanent marker, and then blow the balloon up. And that's how you can kind of see that the galaxies are all moving apart. Everything's moving apart from each other as the universe expands. But what if it expands so much that it kind of pops and all comes back down and then starts again? I mean, these are things that people really don't know. We have the tools to the technology to learn an incredible amount. And like they say, they're hoping with the James Webb to even begin to gather more of these answers. But it's certainly a time where there is more that we don't know than that we do know. Is that a help?
Yeah. It basically says we don't know, and but this is where the physics that we can understand are going.
That's exactly right. Yeah, that's a good way of putting it. Yep. So that's one thing that we can do with by learning about space. Another pretty cool thing that we can do by learning about space is we can start to improve our technology. And so some examples of that, and I chose some examples from NASA since that's where I work, are things like coming up with this solar sail mission. And there's more information if any of these look interesting to you. This idea of this Gateway lunar space station to have, if we start to go back, when we start to go back to the moon and on to Mars. We even utilize some of this technology for here on Earth, for studying like the deep ocean. Then another thing that NASA's pretty famous for, and not just NASA, but European Space Agency, folks that are studying space are what we call these technology transfers or spin-offs. So there's a lot of ways in which things that are being worked on technology for space are also used, say, for things like traffic monitoring for airports, or super insulation. What else do we have here? Controlled propulsion, spraying for food safety. So, and things like a perfect cup of coffee. So we call these space spin-offs when we're looking at some of the various ways in which some of the things that were created for space end up actually being useful for other types of things. Okie dokie. So then, another reason to study space is this search for life. Now, this is a fascinating thing. I mean, most of us are fascinated by this idea of, is there life out there, off of Earth? And the thing is that we just haven't yet been able to prove that there is life. We certainly have some ideas about what we think would be some of the requirements for life, if there is life, but we just haven't been able to come up with any definitive proof. So I like this as kind of starting off. Are we alone in the universe? So far, the only life we know is right here on this planet Earth, but we are looking. And the big question, is there life beyond Earth? We don't even really have a universally accepted definition of what life is. So and you know, that said, we don't necessarily even need one. But when you think about it, because planets have different types of atmospheres, different chemicals, different distances from their host star, you know, the way that life might evolve could look very different from what it looks like for us. So one of the things that we're trying to do is find exoplanets, which means planets that are, you know, not our planet. They're not within our solar system, but you think of all the stars there are out there. There's also thousands and millions and billions of planets. And in the last, I'd say 20 years, we've been able to use our technology to start to explore many of these exoplanets. And basically, at this point in time, we're looking at the exoplanet's atmosphere to be able to better understand if there is if there is the potential for life, and that's kind of life as we know it. So then again, you start to see things like the James Webb and how will we be able to find life, and even this idea, and I really like this, when I used to teach middle school students, I had a whole class on exploratory planetology. And that is when you just take here on Earth, and this is Yellowstone, one of these geysers or mud pots, you have this amazing, these extremophiles that can live within conditions that we never ever thought were possible. So that's where, you know, it could easily be that there are forms of life that we're just not sure about. One of the things that we look at is kind of the Goldilocks zone or the habitable zone when we're looking at exoplanets. So we're looking for some that are not too close, but not too far away from their host star to get a feel for, well, could there actually be life that exists on these planets? And like I say, so far, we haven't found life. I'm seeing that it appears to be a hand up. I don't know if that was a hand up before or if that's a hand up now. But I'll stop and just see if there's a question. Nope, okay. So what this is showing here is this equation called Drake's equation, and I can't even read all the fine print here, but basically what Drake was looking at, and this was probably about 60 years ago that that there was Drake's equation. Drake was looking at the fact that there's all of these different galaxies and all of these different planets, and these are the conditions for life here on Earth. So therefore, it must be possible that there are whatever number of forms of life he came up with. The one thing that makes it a challenge for us is that fact that we do have this expansion of the universe. And so there's this idea that there's actually a really cool group called SETI, S-E-T-I, and it's this international group that's searching for life. And they're basically using, people set their computers, when they're not using their computers, they keep it on this thing called SETI, so it improves their computing power. And they're just looking to see if there's any radio waves out there that are unusual, that could be evidence of an advanced civilization either trying to reach out to us or making noise out there. So I forgot to put that link up there, but I will add it. They're kind of a cool group too, and they're a legitimate group. And so far they have not been successful either in finding life. But the chances for there being life out there are pretty good. Every now and then we hear that they think they found evidence that at some point in time there was some sort of life, like microbial life on Mars. And that could well be there was a lot of water on Mars before it lost its atmosphere. But so far we haven't had definitive evidence. At one point in time, it looked like we had on an asteroid some microorganism fossils, but then they weren't sure if perhaps those microorganisms were picked up where the fossil was found once it hit Earth. So it's just been, confusing in that respect. The data that we've gotten from the rocks that we've looked at while we've had our orbiters, our rovers on Mars, have not given evidence of life. But again, that doesn't mean it's not there. We just have to increase our technology to be able to see if, and again, at this point in time with Mars, we're looking at once upon a time, was there life? Another place where we're looking for, well, there's two other places we think in our solar system could have some sort of, say, microbial life. And one of those is Titan, and that is a moon of Saturn that has oceans. But I think that it also has a lot of methane. And so it would have to be some sort of a life that could live in those conditions. And the other one is Europa. And Europa is one of the Galilean moons of Jupiter. So fascinating some of the ways in which they're looking for life in these various and sundry places. Another reason why we're going out there and looking out into space to better understand space is to better understand if humans can survive out there. You've got, folks right now like Musk who want to get out there and go to Mars and, in part to start to build a colony out there. And also just thinking about, well, when and if we get slammed by an asteroid, or when we eventually, and this is a long way down the road, it's nothing to put on your top 10 list of things to worry about, but at some point in time, our atmosphere, a little bit at a time, is drifting out into space. It kind of gets stripped away by the solar wind. And so at some point in time, we're not going to have enough atmosphere to protect us from the sun's ultraviolet rays. So, and then, eventually our sun is going to shrink and then become a black dwarf. Like I say, that's billions of years away. And I believe with the stripping of our atmosphere, we're talking about millions of years away. So the whole human survival thing is kind of a it's a little bit more of a fantasy than a reality at this point in time. But I suppose it takes a while to start to build up colonies and things like that. The only thing is, not just right now, because of radiation, and I'm going to share a little more information about that in a minute, you'd always have to stay in a spacesuit, and you'd have to stay within these terraformed colonies because of radiation. So let me go ahead and play a short movie for you, telling about the impact and the problems with radiation on the human body.
Space is our future, but space is also a deadly place with poisonous radiation and an increased risk of cancer. We're protected here on Earth thanks to our planet's magnetosphere. But is there a way to create an artificial magnetosphere and shield astronauts? With over half a century of experience sending humans into space, we've learned quite a bit about what it does to the human body. The microgravity weakens the bones, reduces muscles, and puts stress on the organs, but this can be partly compensated by exercise. Time spent in isolation or in close quarters with other astronauts can push people to the breaking point. But this isn't the first time we've learned to work in isolated and dangerous environments with other human beings. Being in space, away from the support of modern society, requires that astronauts have the skills, training, and communication with Earth to deal with medical emergencies, hardware failures, and the inevitable hostile xenomorphs, whether it's a stand-up fight or another bug hunt. But there's one risk that's always going to be there when humans travel out into the solar system: radiation. Powerful solar storms can kill astronauts in days, but even the ongoing background radiation of the universe is going to be increasing their risk of getting cancer through their entire lives.
5,000 years of Chinese music.
All right, so let me close that. Stop. Great. And I'm gonna close that. So, you know, there are definitely some challenges with trying to send people to space. Doesn't mean it's not worth giving it a try, but there's challenges. So another reason why studying space is important is that it also enables us to better study Earth. What you're seeing right there is the satellite that I worked for at NASA. It is called the Global Precipitation Measurement Mission, or GPM. And basically, it's what we call an EOS, Earth Observing Satellite. We have about 24 of these EOSs up in space. In the case of this one, what we have is we have a microwave imager right here, and we have radar, active and passive radar down here on the bottom. And using those different wavelengths, and I'm going to talk a little bit about wavelengths in a little bit here, we're able to measure what kind of precipitation is in clouds as we fly over Earth, and we do that about 16 times a day. And we're also able to use our active and passive, the microwave is what lets us know what's inside the clouds. And then this radar, we get a three-dimensional structure of, as we fly over storms, of how much precipitation is falling in any part of that storm. Now, the cool thing about this is, based on this microwave imaging working so well, we reached out to 10 other satellites that are up in orbit, some of which are not even American. The majority of them are from other countries. They aren't measuring precipitation, but they have a microwave imager on board. So they set to the frequencies that we need, and by gathering the data from them as well as our data, every 30 minutes, we get an updated measurement of how much precipitation is falling from the clouds to the ground. So, and that's just one example. There are so many different examples of ways in which, I'll actually go ahead and I'll show you here, ways in which the satellite technology for Earth observations is being used to help us make Earth a better place. So some of these examples are a big one right now is agriculture. Because from space we can measure how wet the ground is. We can look at it to 5 to 10 centimeters below the soil. We also know how much water is underground. We can see how much precipitation is falling. So it's a great, and we can also see, and this kind of might show a little bit here, but we can also see what kind of vegetation there is. Maybe this map down here talking about putting NASA data to work might be helpful there. Here you're seeing these different colors. Well, those colors are using, I believe it's using infrared technology, which basically is kind of giving us a sense of the heat index there. But that can also tell us what types of crops are being grown there, and just all kinds of ways in which things like also better understanding alga blooms that are happening, just so many ways in which using these Earth observing missions is helping us better understand our home planet. So I always find that pretty cool, and that was one of the things with my job at NASA that I was focused on, is helping people to understand the ways in which we use these Earth observing satellites to improve life on Earth. So another thing is innovation and discovery, and I thought that I would show us a little bit about that let me come back here, about that asteroid that is we've heard about is heading this way. We'll hear from Neil Tyson deGrasse telling us about, as we're learning more about space and we're learning more about asteroids, is this something to worry about? So let me come here and here and here and here, and let me see if that is what I was looking at.
Potentially hazardous asteroids can show up anywhere in the night sky at any time.
It's not Neil deGrasse, sorry.
Oh, this might be something. Oh, you guys, look at that. Right now, it is absolutely a potentially hazardous object. If you guys are gonna be here for a discovery, a PHA is definitely what you want. This is a big rock.
What would an asteroid that is a kilometer in diameter, what would it do if it hit the Earth?
That is likely to end human civilization.
Those objects are big enough to cause what we would call truly global devastation, meaning that they could cause global extinction events. The good news is that we found more than about 95% of them. When we get down to smaller objects, things that are larger than, let's say, about 100 meters across or so, now the picture's not so rosy.
Today, we do not have a complete inventory of all the possible impactors.
There's almost certainly a decent sized asteroid out there that is gonna pose an impact threat to the planet. We're just trying to find it right now.
And that is something that NASA and the worldwide planetary defense community has been endeavoring to do.
There's a huge community of astronomers that start observing it from all around the globe.
Finding asteroids, tracking them, calculating their orbits.
Asteroids don't care about international boundaries.
It doesn't matter where the asteroid impacts. It affects, the entire humanity. In fact, anything alive on the Earth.
I really like that I'm protecting the planet. Let's say we do find something that poses an impact threat to Earth. What next?
The day is coming when Earth will get impacted.
The dinosaurs went extinct because they didn't have a space program. We do have one.
We can't. So why stop there?
We know it will happen. We just don't know when it will happen.
So that's another good reason to be studying space, to make sure that we are keeping track of these potentially hazardous asteroids and have a sense of what is coming our way. Make sure I'm back here. All righty. What else do I have here? So then, of course, there's the economic benefits, STEM careers, being able to learn from this technology, and then even things like video games and computer programming. All of these are things that benefit when we are studying space. So how do we study space? Now I'm going to segue over to that and talk a little bit about this idea of ground-based telescopes versus space-based telescopes. And then I'm going to share a couple of different observatories with you and give you a little bit of a little story about one time a long time ago when I got to go and stay at the Kitt Peak Observatory. So ground-based telescopes are ground-based. We call them observatories because there's generally, when you have a big telescope, it's generally called an observatory. And so these are telescopes that are located on Earth. They can be accessed and maintained and upgraded by technicians relatively easily. They're also much larger, or they can be much larger than space telescopes because they don't have those same space constraints like you'd have when you're putting one out in space. So a space-based telescope is one that is located in orbit around Earth, like the Hubble Space Telescope. The problem with these is they're difficult to access once they're launched, and they can't be easily repaired or maintained, except thank goodness we were able to maintain the Hubble, but you'll see how close it is to the Earth compared and contrasted with, say, the James Webb or the upcoming Roman Space Telescope. So now I'm going to tell you a little bit about the pros and cons for each of these types of telescopes. So location and accessibility, we kind of talked about that before. This idea that, when they're here on Earth, then it's easier to go over and take care of them versus out in space. Then we've got this atmospheric interference. I had mentioned that the winter time is the best time to go out and do observing because we have less of the atmospheric interference to worry about. And so this is something that's always present with ground-based telescopes. The Earth's atmosphere can distort and absorb light from astronomical objects, and that's called atmospheric scene. And basically it can blur objects and it can limit the wavelength of light that are able to be observed. So that's why, for instance, many infrared, ultraviolet, and X-ray wavelengths are absorbed in the atmosphere, and they can't be observed from the ground. And so that's why we need these space-based telescopes. They avoid the atmospheric interference entirely. They operate above the atmosphere so they can get clearer images and they can observe a wider range of wavelengths, including ultraviolet and infrared, that the ground-based telescopes can't. Cost and maintenance, the ground-based are generally less expensive to build and maintain and upgrade. They benefit from easier access for repairs and improvements. And then, of course, the cost of maintaining them is significantly lower. Our space-based telescopes are much more expensive to build and launch. You have to have specialized spacecraft. You've got the launch itself, and then the challenge of designing this equipment that can withstand the harsh environment of space. And of course, once it's in orbit, maintenance and upgrades are more difficult. Right now at Goddard, in this huge clean room we have, which is a good 10 stories, it's the largest clean room in the world. They're building the Nancy Grace Roman Space Telescope. And I actually used to go and watch when they were building the Webb telescope. You can go and just kind of stand up and look down and see all the people there in their bunny suits, these kind of white suits that they wear in order to ensure that they don't have any dust or dirt that's going to get into the equipment, because once we send those up there, then there's no bringing them back, and they're actually going to be impossible to be able to fix. Fortunately, with the Hubble, we were able to go because it's in low Earth orbit and fix it, but not true of these other ones. So I thought I'd stop for a minute and talk a little bit about the electromagnetic spectrum. And unfortunately, my notes are hidden from me. I can't seem to find a way to get to them. So I'm going to do the best I can to explain this without having my notes in front of me. So with this electromagnetic spectrum, it's basically looking at the way light energy travels. And so we're used to visible light that we can see. And there we've kind of got that Roy G. Biv, the different colors in which we can see light. But even if we can't see light, it still exists. It's still these photons, these packets of energy. Some of these, like radio waves, can penetrate Earth's atmosphere, and so can visible light and what we call the near infrared. But microwave, ultraviolet, X-ray, and gamma rays, those don't penetrate Earth's atmosphere. These are showing us basically the sizes of these different waves, and the longer the waves, the kind of less powerful they are. So we've got our long radio waves, and then we've got our microwaves, which are the kind of microwaves that are in microwave ovens. Infrared, those are what we use in our controllers. When we stand away from the TV and we press the button and make the TV go on, that's basically using infrared information and data. And this is kind of telling us the microhertz at which it's measured, the size of the wavelength. So then our ultraviolet, X-ray, and gamma rays, they have a lot more energy, and they're a lot smaller. So I'll leave that there. Then over here, this is kind of a similar sort of thing, but just showing us it in a little bit of a different way. And the reason I'm showing you this is I'm going to be telling you about the fact that different telescopes can measure things either in visible light, and that's what the Hubble is doing. That's what the telescopes that we own are doing. We're looking at things in the night sky in visible light. But we've also got infrared telescopes, and we've got radio telescopes that are looking for and listening for the sounds and gathering that data out there. And we have X-ray telescopes. So they're gathering different kinds of information. And I'll have some videos up ahead that will explain why we would use one of these different types of telescopes for certain purposes. So here's where this kind of goes into that. Observational range. Our ground-based are great for optical and radio astronomy. But again, we've got those atmospheric conditions and the availability of clear skies. So basically, and you'll see this when I show you some of the different Earth-based telescopes, that high latitude, like you'll hear about Mauna Kea, the very large telescope array in Chile, even where I was at in Kitt Peak, they're generally up on mountains because that high altitude then decreases how much of the atmosphere they have to look through. So our space-based telescopes, depending on what kind of instrumentation are on them, they can observe all wavelengths of light, the infrared, the ultraviolet, the X-ray, because they're not affected by Earth's atmosphere. And so that gives them a broader observational range, and they can detect fainter signals from distant parts of the universe, kind of like looking for those Cepheid candles and seeing how far they're moving apart. Image quality, so our ground-based telescopes, even with the advanced adaptive optics, trying to reduce that atmospheric distortion, the image quality can still suffer compared to these beautiful space-based observations. But of course, advances in technology are improving the clarity of these images. And then with our space-based, we've got much clearer and detailed images, especially in the wavelengths that are absorbed in the atmosphere, like ultraviolet and infrared. Almost done with these pros and cons. Ground-based telescopes, even with the adaptive optics, the image quality can still suffer compared to the space-based. And then we just did that. Okay, so I said that I was going to tell you a little bit about, and we'll go to the websites of a few of these telescopes. Mauna Kea is pretty cool. I've never been there. Someday I want to. I haven't even been to Hawaii yet, so that's on my short list of places I have to go. And the neat thing about some of these different observatories, some of them are operated by, say, NASA, European Space Agency, and some of them, like Mauna Kea, are groups of nonprofit independent institutions who pooled their money together and were able to use the land and then build these huge telescopes that do a variety of different things. So at Mauna Kea, they have optical, which are just basically the kind we're used to, the visible telescopes, near infrared, submillimeter, and radio astronomy facilities. And they're able to not just get pictures, but a big thing when you're using telescopes now, when you're looking out into the universe, is to use what's called spectroscopy. And that's basically where you're gathering data that lets you know what chemical properties, what different types of chemicals are in the atmosphere of the areas in which you're looking. And so some of the things that they've learned with their instruments at Mauna Kea is they've been able to find potentially habitable Goldilocks exoplanets, the weather and moons of planets within our solar system, nearby supermassive black holes, and information on the history and origins of the universe. So no small feat there. And let's take a look at the Mauna Kea website. And of course, all of these I have put on that list, so you can go and look more when you get a chance. So basically, Mauna Kea is built on a shield volcano in the middle of the Pacific, and it's at about 13,803 feet. So nice and high up there, up above the atmosphere. These are some of the things that they're looking for when they're building an observatory, a ground-based observatory, things to keep in mind. And then if you go down a little further, you can learn more about how they utilized their technology, their telescopes, to be able to better understand some of these different concepts. So I won't go into them now. Some just really cool, amazing things that they're doing there. And another pretty neat thing that they do at Mauna Kea is they're very respectful of the Hawaiian culture. And there's a lot of programs there and a lot of activities where they're looking at Hawaiian culture and kind of native understandings and blending those in with current day understandings of some of the various things that they're seeing in the out there in the atmosphere. Okay, then we have what's called the Very Large Telescope. I just think that's a great name because that's exactly what it is. And very British and kind of coming up with something like the Very Large Telescope. So this is run by the European Space Agency. However, it is in Chile. It is a visible light observatory, and it is one of the world's most advanced optical telescopes. And basically, it's got these 4 different telescopes that have these huge mirrors, and they're able to make them work together. And so that's how come it's called the Very Large Telescope. And let's take a look at this Very Large Telescope. Another amazing observatory to visit, I would think. All right, come back to this and this and that. So moving on, we've got our Very Large Telescope, and then I wanted to tell you a little bit about Kitt Peak. So when many years ago, and I'll open this up so we can take a look at this while I tell you, I happened to, I was a classroom teacher at that time. So when was this? 2005. So many, many years ago. And I had this opportunity to take this class that was virtual and lasted for a whole semester. And then in the class, basically, we learned about observational techniques. And then we were put into different groups where we have focused on one kind of thing that you could see in the night sky. So I got put in a group to look at quasars and active galactic nuclei, which are apparently when you have a supermassive star and it explodes, sometimes it will become a black hole. And then sometimes it's not big enough to become a black hole and it becomes a quasar, and it's shooting energy from either end of it's, if you imagine it kind of like a pancake, from either end it's shooting energy. And so basically we were looking at these quasars, and we were looking at the spectrum from these quasars, and we were looking at seeing how fast they were moving, either away or sometimes toward us, depending on where they were and where Earth was, because that's, of course, everything was from Earth. And we were doing that based on this spectrum. And it was it was a lot of math, a lot of very, very fine focused work, but we also had a lot of fun. When we were there for about a week, and while we were out there, it was so neat. We would be up all night, and we had these rooms where they had really, really good curtains, so that we would sleep during the day, and then we would get up and we'd kind of have we get up when it was I don't know, probably around 5 o'clock in the evening, and we'd have our dinner, and then we would go out and we would do a little bit of sun observing, because they had this marvelous solar telescope. So we would go to the solar telescope and we would look at the sun going down. We were always looking for the green flash. I don't know if any of you have ever seen the green flash. I have looked for it time and again. I haven't seen it yet, but apparently sometimes when the sun is going down below the horizon, sometimes there's this green flash. I forget what causes it, but it's really cool to see. And unfortunately, we weren't lucky enough to see it while we were there, but the solar telescope was way cool. And if you ever get a chance to go, some places have solar telescopes. It's really cool to look at the sun, particularly now while it's in solar maximum and there's a lot of sunspots. But with this telescope particularly, because it was such a good one, we were able to see solar flares and mass coronal ejections, and it was just crazy cool. Another thing that I loved is standing out on the big 4.5 meter telescope. We could stand out there and it would just slowly be slewing around. And there, the night sky was so dark, because you never even had flashlights when you were there. You just had little red lights, and there were some little red lights on the ground, so that's how you could see your way around. But there were no lights, and it was wonderful because the night skies were incredible. You could just see the Milky Way just dripping down. And so I remember with a girlfriend, we would hold on to the side of the big telescope as it was slewing around. And it was just like somehow we were magically going, around through the stars. It was an incredible, magical moment. But another kind of a magical thing happened. So we were out on this on the big telescope, and we were learning how to take telescope images on this 0.9 meter telescope. And we decided that we would look at the Whirlpool Galaxy. So here's what the Whirlpool Galaxy looks like. And while we were taking this image, one of the astronomers who was working with us, we had these fabulous astronomers who work at Kitt Peak, noticed that there was an unusual light that was coming up there. And apparently what happened is at the set, right before we had seen that, see if I can make this big enough to see, that 2 nights earlier, a German amateur astronomer had looked at M51 and had seen this brand new supernova, a massive star that suddenly explodes. And he had been in the process of reporting it, and we saw it too. Now, we saw it 2 days after him, but nonetheless, I guess we got credit for having been the second folks to have seen this supernova explosion. And we would not have known, like I say, if it hadn't been for that wonderful scientist who was there letting us know what we were seeing. But it was incredibly cool. And it's one of those sorts of things. I was glad when I was a teacher that I always took advantage of these opportunities, because there was just so many amazing things, like this opportunity to go to Kitt Peak. I did see on their website, and that is, of course, in the paper in our syllabus, that you can plan a trip there. Of course, it's not cheap, but you could plan a trip there, and you could go and you could do some observing, and it really was just an amazing opportunity. And so here you see these are some of the different telescopes that are there. This is the solar telescope. That one was just so cool, but they all were. So, take a look at their website and see some of the things that they're doing there. Basically, in many of these independent observatories, scientists have to buy time. And in order to buy time, they have to have research proposals and have gotten enough money so that they can go and they can be there. Now, they're always taking a risk that perhaps during their allotted time that they have to spend on whichever telescope they have paid the money for, if the weather's crummy, then they're kind of out of luck. They've got to wait. I think they have kind of like a waiting list, and they can, kind of come back without it costing a fortune. But it's some pretty it's incredibly exciting to be around these scientists, these astronomers who are just so passionate about what they do. And down to every single one, we're just so excited to have people with whom they could share their experiences and kind of turn us on to what they were excited about. So it was just an amazing opportunity. So now we're going to leave our ground-based scopes, and now we're going to head up and take a look at our space-based telescopes. And of course, the Hubble is the one we've all heard about. That one was launched in 1990, and it's in what we call low Earth orbit. The satellite that I work for is about, now it's 400 miles above Earth. We had it at about 350 miles above Earth. And then with solar maximum, there was so much solar wind the last year and two, pushing it down, that we had to use some of our very, very precious fuel. Because once we run out of, we do have solar arrays, but we have a certain amount of fuel which we have to save in order to have a controlled reentry into Earth when we determine that our satellite is no longer able to gather data, because they get old just like cars do. Eventually they rust, and they're just no longer functioning like they should. So in any case, we had to use some of our valuable fuel to boost our orbit up and get us up to 400 miles above Earth, knowing that with solar maximum, we're going to be pushed down a little bit more. So in any case, I digress, but kind of cool stuff. So this Hubble is in low Earth orbit. And the images that we have seen coming in have been, nothing short of being amazing. It we're used to some of the pictures from the visible, but it also collects data in the ultraviolet and near infrared. And that's useful because that way it's able to see through the dust and see through the clouds. Now, when we see the images, we're seeing cleaned up images. We're not seeing exactly what the Hubble took, particularly if it's in the ultraviolet or near infrared. But we have, and one time I had this chance to listen to one of the guys, happened to be a guy, I'm sure there's women too, who take these Hubble images and James Webb images, and they make them palpable for people to look at. And the process through which they go through was really fascinating. I can't remember all of it, but I'm sure it's a sort of thing that's online were you ever interested, to learn more about how they take these images and clean them up so that when we're looking at them, it's making more sense to us. And this is a collaboration with the European Space Agency, which is kind of cool. So let me stop that for a sec. And we're going to take a look at this. I thought was pretty cool because it shows how you utilize both the Hubble Space Telescope, but also the James Webb data, and sometimes even data from what's called the Chandra X-ray Observatory, which I'll tell you about, how we can pool those together to better understand what it is we're seeing out there in space. Oops, I didn't mean to do that. And
As we zoom through the cosmos, two galaxies emerge from the darkness, entwined in a gravitational interplay. On the right, NGC 2207, the larger of the pair, exerts a gravitational pull on its smaller neighbor, IC 2163, seen on the left. Though they haven't yet merged, their close encounter has begun to pull and twist their spiral arms, causing tidal extensions, ethereal tendrils stretching across the void, marking the early stages of their cosmic interaction. These galaxies reside 114 million light years from Earth, with NGC 2207 spanning 143,000 light years across, and IC 2163 measuring 101,000 light years, about the size of our own Milky Way. What makes this image even more spellbinding is the blend of data from two powerhouse telescopes. Webb's mid-infrared view captures star formation happening right now, while Hubble's visible and ultraviolet light reveals young stars that have recently burst into life. It's like peering through two windows in time, layered together to offer a richer view of these galaxies' evolution. Notice the striking blue clusters scattered throughout the image. These are clusters where stars are forming at a furious pace. Hubble highlights these stellar nurseries, while Webb's mid-infrared vision casts a ghostly red glow, illuminating the dusty regions that envelop the stars. Together, these views give us a haunting look at the galaxies wrapped in luminous shells of dust. These galaxies are star factories, producing new stars at a rate 5 to 10 times faster than our Milky Way. Each galaxy has witnessed several supernovae, massive cosmic blasts that have left their mark, spreading new elements into space in the process. These powerful explosions may have carved new pathways for fresh star formations, visible as the intense blue patches scattered throughout the image. And those blood-red lines, they're likely shock fronts, zones where the galaxy's materials have collided and compressed, creating a spine-chilling reminder of their turbulent interaction. This spot, known as Feature I, is a hub of rapid star formation on the outer arm of NGC 2207, glowing even more brightly than the galaxy's core. Though it looks dusty and quiet in visible light, it's actually the galaxy's most active area, a mini starburst region where stars form at an astonishing pace, and traces of ancient supernova explosions echo through the cosmic landscape. In a few million years, these galaxies will merge, their fiery cosmic rendezvous culminating in a single stilled galaxy. This image, brought to life by the collaboration of Webb and Hubble, exposes galactic interactions and star formation in chilling detail, offering us a rare glimpse into the universe's dark mysteries.
I know that sort of thing just simply blows my mind. This, you know, that we're able to utilize technology to this extent nowadays to be able to know these things. Simply amazing. So moving on to amazing. So the James Webb, like I say, I was able to watch this being built over there at Goddard Space Flight Center. Sometimes they have open houses, not very often now. They're all kind of trying to cope with funding issues. But if you know anyone who works there, if you can ever get over there, you won't see James Webb anymore, of course, but you could see the Nancy Grace Roman being built. James Webb, way cool. See this thing here, this big gold thing? That's about the size of a tennis court. So it's this funky looking kind of layered telescope that is way, way out. So we could never go and work on fixing this. It's at what we call Lagrange point 2. There's these various Lagrange points when you get out in space, and it's about 1.5 million kilometers from Earth. It's a joint project for NASA, European Space Agency, and I'm trying to remember what CSA is. It's not coming to me right now. So it was launched on Christmas of 2021. Certainly something they worked hard during the pandemic to get this to actually launch, and it was so delayed, and it ended up costing a lot of money. So they were bound and determined to get it off, and indeed it did. And what it's basically doing is it's exploring the universe in infrared light. So let's take a look here. And what I wanted to show you was this information here. So here, some of these key facts I'm going to put on my glasses as I go through this. Some of the things that make it different. And I love this too when I'm working, say, even with the satellite mission I work for, looking at what came before to get a feel for how they modified things with technology to do things a little bit differently. So of course, when we looked at the picture of the Hubble, certainly this James Webb looks so much different. And when you see Nancy Grace Roman, very, very different as well. So here it's so big that it had to kind of origami style fold up to fit in the rocket. And of course, that was one of those things that was incredibly wonderful that it all unfolded as it should, because that's a huge deal. It's about the 1.5 million kilometers from Earth, and it has this huge solar shield because even though it's far from Earth, but sorry, from the sun, it's 1.5 million kilometers from Earth. It's 560. But it's still, you have to ensure that the part that's facing the sun is shielded. So there's that what that gold shielding is there. And it's able to look back the 13.5 billion years ago, kind of looking back and getting a baby picture of what the universe used to look like. Because even though it's far away, it's still not able to see in real time what's happening. It's like the same when we're looking at the stars at night. We're looking and seeing what they looked like, depending on how many light years away they are. We're looking back and seeing what they used to look like. As the woman was saying, Betelgeuse may have already gone supernova, and we won't know it for a while because it takes the light so many years to come down to Earth. So it's going to at least look back and see what it looked like right after the Big Bang. And so basically some kind of cool things about the James Webb. You can come to this website, and of course I have that there for you, and learn some of the latest news, see some of the latest images. And I like when they have the featured image, they go ahead and either have a video or they have some written information to give you an idea of, as you look at that pretty picture, what is it exactly that you are seeing? Because that's not always readily apparent. All right, then there's also the Chandra X-ray Observatory. This one was launched in 1999, so a couple of years before James Webb. And what it does is what's called X-ray observatory. Now, because X-rays are absorbed by Earth's atmosphere, Chandra is about 86,500 miles up in space to be far enough up so that it is able to measure the X-ray information. It has 4 very sensitive mirrors that are nested within each other. And then as the energetic X-rays strike the insides of those hollow shells, then they're forced into these electronic detectors that are at the end of this optical bench. And so depending on the kind of detector that's being used, they can get very detailed images or spectra of a cosmic source. So let's take a look at a couple examples of what this means when they say that they're looking at this spectra. So here we are at the website, and here, just look at, this is an amazing image in this case of, I'm sure it's a star-forming location. It's the deepest X-ray image ever taken of this spectacular star-forming region called 30 Doradus. And then that was taken on the 12th of February. So lots of neat things you can go into here. I found this Listen to the Universe really, really interesting. And I actually have something from that on our next slide. So I'll stop sharing there. I know I'm giving you so much stuff to go and take a look at when we don't have class that you'll never run out of bedside reading, even though I'm sure you never do anyway, because you're all people who are interested and then therefore interesting. All right, let's take a look here at one of the things that they were able to discover with Chandra.
Visit Chandra's beautiful universe. Perseus and Centaurus clusters. Astronomers have taken a crucial step in showing that the most massive black holes in the universe can create their own meals. Data from NASA's Chandra X-ray Observatory and the Very Large Telescope, an optical light telescope in Chile, provide new evidence that outbursts from black holes can cool down gas to feed themselves. This study was based on observations of 7 clusters of galaxies. The centers of galaxy clusters contain the universe's most massive galaxies, which harbor huge black holes with masses ranging from millions to tens of billions of times that of the Sun. When feasting on gas, these black holes power outbursts of particles in the form of jets. The results support a theoretical model that astronomers have that shows that outbursts from the black holes trigger hot gas to cool and form narrow filaments of warm gas. Turbulence in the gas also plays an important role in this triggering process. According to this model, some of the warm gas in these filaments should then flow into the centers of the galaxies to feed the black holes, causing an outburst. The outburst causes more gas to cool and feed the black holes, leading to further outbursts. This result also provides new understanding of these gas-filled filaments, which are important not just for feeding black holes, but also for causing new stars to form.
Cool. And, next slide. So then this is the telescope that's being built now, obviously hasn't launched yet, named after NASA's first chief astronomer, the mother of Hubble Space Telescope. Her name was Nancy Grace Roman. This telescope is going to have a field of view at least 100 times larger than Hubble, potentially, measuring light from 1 billion galaxies over its lifetime. It will also be able to block starlight to directly see exoplanets and planet-forming disks and help us complete a statistical census of planetary systems in our galaxy, and then also help us better understand. This says settle. I don't know that we'll necessarily settle, but better understand these ideas of dark energy, exoplanets, and infrared astrophysics. And you can also go to that site to learn a little bit more about what that is planning to do. And so basically kind of my parting words are, with astronomy, I had to learn to tolerate a lot of ambiguity to get myself started in astronomy. I also never had a physics class, and that's one of the things that I would definitely like to take a physics class. Now that I understand the ways in which physics are used to be able to do all of this, I would love to know the inner workings of it. I didn't have that, and I kind of came into this, like I say, my 10-year-old said, "Mom, go out and let's look at the stars." And it just blew my mind, and I had to learn more. And hence, I was very fortunate to get accepted at Johns Hopkins and get this Earth Space Science certification. So, by staying curious, and now that we've got the internet and we, have learned how to vet good sites and kind of what is fake news versus what is real, certainly the links that I have given you are all based on legitimate sites. When I was looking up some information on space colonization, I found some curious sites, but nothing that I put on there. I did give you one, though, that is an international group of people who are looking at space colonization. So kind of curious. When you go out into the night sky, remember, take some time, take a good 10 minutes to let your eyes dark adjust. If you can go somewhere where you've got better skies, where you've got darker skies, that's great. Certainly helps. But even in your own yard, look at something like Stellarium to find out what you're going to be able to see. take your smartphone out there that has that way that it will put the red light on so you're not blinding yourself after you've let your eyes dark adjust. And then just try to find a few objects. I have certainly done taking, say, the Big Dipper and then using that to be able to find other constellations. And then I've also done the one where you take Orion and find others. That's how, when I was out there with the astronomers and we were looking for specific star clusters, we would be out there, like I say, sometimes literally for hours to make sure that we had gotten what we were looking for. But don't aim so high that you end up frustrating yourself. And do take advantage of these cool places around here that offer observing nights, because there you're going to have real professionals who know what they're looking for and can guide you better. And then in the fall, I'll offer this class again. Maybe it won't be quite so cold. And if I do it something like October, before we get super busy with the holidays, perhaps it will be a little bit better observing weather, who knows? And then I'll also create a class on stars and galaxies. So if this kind of tasted like more, then I will come up with another course that goes on from here. So I hope that you enjoyed this class. Oh, good. Thank you so much, Mauricio, for adding some information there. I'm going to go ahead and stop